In this lecture, we're going to be discussing the periodic table history. This is Unit 2, Notes 3. We're going to talk about the scientist that helped contribute to the structure of the periodic table. We've probably seen periodic tables before in textbooks, like science textbooks, maybe in science rooms. They have a big poster of it, or even on TV. There might be shows that have periodic tables. So you've definitely seen one of these before. And again, we're going to talk about why does it look the way it is? Why are the rows and columns different? And why are they sometimes color-coded, okay? To start us off, we're going to talk about a very important individual, and that is this guy with long hair, untamed hair, and definitely looks like a chemist, if you ask me. This guy's name is Dmitry Mendeleev, and back in 1869, he started creating a table of the different elements that he was aware of, okay? So a long time ago, scientists were aware that there were different elements, and then they had different properties, and that they would do different things, right? So he was kind of the first pioneer to organize all of the elements onto his own little data sheet, and he kind of created like the early version of an Excel spreadsheet, something that might look like this, where he would organize all of the elements based off of the number of protons they have, and also their characteristics. So Dmitry Mendeleev definitely knew about the elements, and he knew how many protons and electrons they had and how they would react with one another. And based off of those characteristics, this is the Excel spreadsheet that he came up with. Obviously not in Excel, but kind of like, just a spreadsheet on a sheet of paper. And he knew that there were some blanks because at that time, he hasn't discovered all the elements yet. They haven't been discovered by other scientists either. So he knew there were elements that theoretically existed that had a certain number of protons, a certain number of electrons, and that they should behave in a certain way based off of a pattern that he noticed. Okay, so for instance, there are some of these pink blanks here that you can see in this spreadsheet. And he knew that there was an element, number 44, that had 44 protons. Its atomic number is 44, therefore it had to have 44 protons. Yet to be discovered, didn't know what it was, and but he could kind of make predictions. And the way he did that is that he compared element number 44 to calcium and titanium. Okay, he also compared it to possibly aluminum, and there might be a relation going up and down in the column. So he did that, and these are the predictions that he came up with. He called this element back in 1871 ecosilicon. Okay, ecosilicon is not the name of this element. The correct name is germanium, discovered in Germany. Probably why Dmitry couldn't discover it, because he was all the way in Russia. So germanium, these are the actual properties in this column, and the predicted properties that Dmitry Mendeleev was able to predict are right here. And you can actually see it's very, very close. He said the atomic weight was 72, where the weighted average is 72.59. The density, he said it was 5.5, where it's actually 5.35. Very close. Valence electrons, we'll talk about that later, but that's an easy thing to predict. 4, so he was right there. He said it was a metal and that it would have a dark gray color, but the actual property is that it's actually gray-white, so maybe a little bit off, not too far off. Does it form an oxide with 2 oxygens? In this case, he said yes, 2 oxygens, and that's what it actually does. It forms a reaction of 2 oxygens. With chlorine, there's 4 chlorines here and 4 chlorines here. So he was able to kind of predict a lot of these things, and he was actually really accurate. And so we call him like the father of the periodic table. He kind of created the first version of the periodic table. It was later then advanced by other scientists, most notably by a scientist by the name of Henry Moseley in 1913. He created this version of the periodic table. But you notice that it's very wide. It's no longer like that nice spreadsheet format that Dmitry Mendeleev had, but it actually makes sense to have it this way, and we'll talk about why. And this version of the periodic table might start to look a little bit familiar, kind of close to ours. The main difference between this version that you see on the screen and our current version is we took this middle section right here and we kind of moved it to the bottom, okay? And then we scooted those 2 rows over. So now it should start to look really familiar. This is the current version of the periodic table that we have. In the earlier versions, all of these elements on the bottom, the ones that start with U and have 3 letters, these were like unnamed elements, and then these ones were yet to be discovered. But as of today, we are up to element 118. At the time of this video being made, we are up to element 118, and they are all named as well. So we'll take a look at that updated version of the periodic table later, but what we're going to do now is talk about why is this periodic table superior to Dmitry Mendeleev's periodic table? Why did Henry Moseley create it like this? Well, there's a lot of reasons, and we're going to talk about those reasons for the next couple of lectures. But the big reason is because, again, we want to look at characteristics and how elements are going to behave in reactions. And so they're grouped together in like these families in which they behave very similarly. Okay? Most of the elements that we encounter are going to be metals. So this is just kind of like a breakdown. If I erase all of the element names and just kind of categorize them as metals or non-metals, about 2/3 of all of the elements are metals. Notice that I skipped the radioactive elements on the bottom. These ones on the bottom, these are radioactive. A lot of those are metals as well. So they belong here. They are actually metals. So about 2/3 metal, about 1/3 non-metal, and then like there's this weird middle section, this blue section that has like this staircase. Those are called the metalloids. Those are going to have properties of both metals and non-metals. We're going to talk about those later. But basically, they are kind of like this transition area between the metals and the non-metals. You might notice that there's this one non-metal up here in the corner that's categorized with next to all the metals. This is hydrogen. In some experiments, hydrogen has been able to show metallic properties, but we consider it a non-metal. But we still group it here just because it shares properties with a lot of these, or it shares the same number of valence electrons as these elements over here. We'll talk about what that means later, the term valence electrons. All right, so the periodic tables can be grouped in periods like this. So if we take a look at the color, red, orange, the Roy G. Biv colors right here, that's basically how we group them. That's why we call them the periodic table. Just like a school schedule that you might have received in the beginning of the year shows you a complete list of all of the periods that you have throughout the day. This is kind of like the same thing. It's showing you all of the periods throughout the periodic table. And then we also can group them into groups. And grouping them into groups rather than looking at the periodic table as periods is actually way more beneficial in terms of understanding how the elements are going to be reacting, how many valence electrons they have. All of that information is really useful if we look at the periodic table as in groups. Now, in the terms of energy, you would want to take a look at periods. So, for instance, if we go back a slide and take a look at the periods of the periodic tables versus groups, the higher energy elements are going to be towards the bottom, and the lower energy ones are going to be towards the tops. Like hydrogen and helium, those are going to be like the lower energy because they have fewer electrons. And then a lot of these are radioactive because of the number of neutrons and things like that. So moving forward, here's another version of the periodic table showing you what these samples might look like. Some of them actually have pictures of people versus the actual sample, maybe because this substance is just too unstable or we haven't been able to take a picture of it. And some of the elements have like flags or something to notate where it was discovered. Notice, again, a lot of them do look metallic because 2/3 of the elements are metal. A lot of them we do use in daily life, like titanium and nickel, copper, zinc, silver. A lot of these are used every single day. And then a lot of these over here are going to be gases, like fluorine, chlorine, bromine. All of these noble gases, xenon, krypton, argon, neon, so on and so forth. So just an interesting periodic table showing you what they might look like or who discovered them. Like we have Marie Curie for curium, Albert Einstein for Einsteinium, so on and so forth. And we have actually Mendelevium for Dmitry Mendeleev. All right, so moving forward, here's an actual view of the complete periodic table at the time of this video being made. Theoretically, you could add more rows on the bottom. You can have like element 119 be under francium right here, but that would be an extremely unstable element. So probably unrealistically in our lifetimes will we see more elements come out of this. But we have currently 118 different elements, and combining these elements into different combinations and compounds can result in a variety of materials being made. And all of these elements, these 118 elements, compose everything that exists in our universe, which is really crazy to think about. Notice, though, that there's really nothing here. And there's a reason for that. And that reason is that because we structured all of the elements on the periodic table based off of how many valence electrons they have, which we'll learn about in a minute, and also the orbitals, which we learned about in the electron configuration notes in notes 2. So if you remember like the shape of the orbitals, all of these elements over here on the far left, they are going to have like this spherical shape, the s orbital. That's what they look like on the outside. They have this s orbital, and all the ones outlined in purple, except helium. Helium has an s orbital, but it kind of shares the same properties as all of these elements, so it kind of behaves the same way. But because of the number of electrons it only has an s orbital. Okay, so that's like the s cloud, and then like notice these ones over here are going to have a p cloud, so all of these have this like p shape. So that's why the periodic table is kind of structured like that as well, so that we can identify their shape and also how many valence electrons they have. All right, so let's take a look at example of oxygen. We're going to do a little bit of a review of the electron configuration. And oxygen, if you can find it on this shortened version of the periodic table, is actually right here. Okay, and the number of electrons that oxygen has is going to be about the same as the number of protons. How do you identify the number of protons? You just look at the atomic numbers. The atomic number here is 8. Because I have 8 protons, that means I have 8 electrons. So if I have 8 electrons, let's do that electron configuration to fill out all 8 electrons. So we have 1s2, so that's 2 electrons, 2s2, that's 2 more electrons, so that's a total of 4, and then 2p4. Okay, so that's a total of 8. 2 plus 2 plus 4 is 8. And notice here that that is the electron configuration. There is actually a periodic table that will tell you the ending of the electron configuration of all the elements. And notice that there is a pattern. There's 2s2, 2p1, 2s2, 2p2, 2p3, 2p4. So it goes up by 1 throughout the entire thing. And also notice that the energy levels, all of these on the first row, they end in 1. So like you have 1s1, 1s2. All of these start with 2, or they end in 2, 2s1, and they end in like 2p6. Over here in the third row, 3. They all have 3 in it. So there's, again, a reason why we structure the periodic table. It's based off of how many electrons the atoms are going to have. All right, what about, let's do another one. Let's do magnesium. Magnesium is number 12 on the periodic table. 12 protons means 12 electrons. And if we do that full electron configuration, what you can actually do is just write down the endings of whatever you have on the far right and then put in the next one. So if you remember doing the shortcut method in the electron configuration notes, where you like have the shortcut where you go up and then to the right, and that element can substitute for like the first few electrons. This is kind of related to that. So what you can actually do in this scenario is just write down the endings of all of the elements on the far right side, and then when you get to the row that has your element, you can just write that one down. So in this case, we're going to write 1s2, so we're going to write that one, and then it has all of these electrons, so it has 2s2, and then it has all of these ones as well, 2p6, and then finally, it doesn't get to 3p6, it actually stops right here. So it's kind of like reading a book, left to right, and then finally left to right, and then you end in 3s2. So that is the electron configuration for magnesium. So the second part of the notes, we're going to talk about this term that I've been throwing around, valence electrons. What are valence electrons? Well, valence electrons are going to be the electrons on the very outside of an atom. Okay, so when we talk about that electron configuration, we have like the 1s2, 2s2, 2p6, 3s2. The very last energy level, so in the case of magnesium, let's go back a slide. In the case of magnesium, the largest energy level is going to be this, 3s2. This is the highest energy level. Just to review, how do we determine the highest energy level? It's going to be the biggest big number. So the big numbers are 1, 2, 2, and 3. 3 is the largest one. That means that's the highest energy level. Okay? Once you've determined what the highest energy level is, the next step is to determine how many electrons do you have in that highest energy level. So in our case, we have 2 electrons in that highest energy level. Okay? So that means magnesium has 2 valence electrons. Okay, so the valence electrons are the ones on the largest energy level. They're the ones actually going to be on the outside of an atom. So what's the importance of valence electrons? Well, valence electrons, again, are the ones on the outside, but the thing that's important about that is knowing the number of valence electrons will tell you how an element is going to react. Is it going to react violently? Is it going to try to attach to anything that it could possibly can? Or is it going to be stable on its own? So the valence electrons are actually a very crucial part of knowing how an element is going to behave. Is there a shortcut that you can use instead of having to write out the electron configuration for all the atoms? Yes, there's actually a very useful shortcut. Remember, the whole periodic table is based off of the orbitals and it's based off the electron configuration. So there's a shortcut to figure out how many valence electrons it is, and all you have to do is look at the group number. Okay? So for instance, if I want to take a look at silicon here, silicon is number 14 on the periodic table with 14 electrons. How many of those electrons, the 14 electrons, are going to be on the outside? Well, if you don't have a periodic table that doesn't have the ending, so over here 3 is the highest energy level, and since 3 is the highest energy level, I have 2 electrons here, 2 electrons here. That means there's 4 valence electrons. That's one way to go about it. What you could actually do, though, is just look at the column number here. So if the column is 4, that means every element in that column going up and down is going to have 4 valence electrons. Okay? And again, valence electrons are going to be the electrons that are actually doing the reacting. Those are the important electrons. And just some practice here, if we take a look at 1A, column 1A, that means hydrogen has 1 valence electron, lithium has 1 valence electron, and sodium, Na, has 1 valence electron. So by now, I hope that you have your own version of the periodic table, one that's black and white, and probably something to color with, or at least a colored pen, because what I would like for you to do on your version of the periodic table is to write in a certain color the words valence electron pattern. Okay? If you don't have a periodic table, this is something that you can do later, but I definitely still encourage you to do it. I would like for you to write the word valence electron pattern in a specific color. In this example, I chose red. And all we're going to do is label the columns left to right that have the certain numbers on them. So over here, this is going to be column number 1. This is column number 2, 3, 4, 5, 6, 7, and 8. And so what that means, let me explain this really quick before you continue writing this down. What that means is that everything in column 1 in this column has 1 valence electron. Everything in column 2 has 2 valence electrons. 3 valence electrons, 4, 5, 6, 7, and finally 8. Okay? So the maximum amount of valence electrons that you can have is 8 valence electrons. There is one exception, though. The one exception is helium. Helium does not have 8 valence electrons. Even though it is in column number 8, it does not have 8 valence electrons because it only has a total of 2 electrons. It's element number 2. That means it has 2 protons. Therefore, it has 2 electrons. Oftentimes, I get the question, why did we put helium in this corner right here instead of putting it right next to hydrogen? Well, it's because helium actually doesn't behave like any of these elements here. It actually behaves much closer to these elements right here. So that's why we put it there. Okay? So helium belongs with those on the far right. Those are called the noble gases, and we'll learn about those later. The other question that I often get is, why are there no numbers in the middle? Okay, well, it's because these elements, most of these metallic elements, actually don't have a pattern for valence electrons. But later on, we will learn how to write down how many valence electrons they have, or to figure out how many valence electrons it has. Okay, so just to recap, valence electrons, those are going to be the electrons on the very outside of the element. They determine how an element is going to react, or how stable it is, and they can be determined simply by looking at what tall column the element is in. So you just count the columns left to right, 1 through 8, and that's how you can determine how many valence electrons that element has. The other thing I want to mention, and this is going to be the last part about 8 valence electrons, we're going to learn more about this later when we get to like reactions and actually mixing elements together. But when elements want to mix together and form new compounds, they want to form a compound that is stable, and usually compounds that have 8 valence electrons are pretty stable. Okay, so for instance, if I wanted to take sodium, Na, which has 1 valence electron, I would probably want to mix it with something that has 7 valence electrons. So sodium and chlorine, for instance, chlorine has 7 valence electrons. 1 valence electron plus 7 valence electrons will give you 8 valence electrons total. Sodium and chlorine mix pretty regularly. When you form them together, it's sodium chloride, which is table salt. Is a pretty common thing. Just like how magnesium, which has 2 valence electrons, would possibly mix with oxygen, okay, which has 6. 2 plus 6 gives you 8. All right, so that's just another example. Another example is that you could take 2 lithiums, for instance, and 1 oxygen and react those together. So 2 lithiums, 1, 2, and then plus another 6 will give you 8. All right, so what about the electrons or the elements that already have 8 valence electrons? These are called the noble gases. They actually don't really do a lot of reactions at all. Because they already have 8 valence electrons, they're kind of comfortable being by themselves and not reacting with anything because they're very stable. Again, we'll learn more about this later. It's just the last note that I want to add on valence electrons. So what I'd like for you to do now is take about 10 minutes or so and work on practice problems 1 through 8. 1 through 7 in your notes are going to be just short answer, a couple of words each. You might need a periodic table to answer some of them, so try to find one in the class or maybe just look one up online. And then you will need probably a periodic table as well to fill in the chart for question number 8. There's going to be a separate video going over these practice problems, and that could be found in the module.